Life, a force that can be experienced all around you. In the sky, underground, and on the Earth's surface, we find life everywhere, in all manner of forms. Since the very origin of the universe, even the smallest of its particles has danced to the rhythms of this life force. Regulated by that unique phenomenon that you and I know as motion. The laws of motion have driven the dance of life since the dawn of creation, but it was only some 300 years ago that man began to understand these driving forces, with the arrival on the scientific scene of a unique mind of unparalleled genius, Sir Isaac Newton. Newton made a simple but profound observation. Every object remains either still or in a state of uniform motion until it is acted upon by an external force in one form or another. This external force increases or decreases the object's velocity to a specific extent that can be determined precisely. But the question that arises is, how exactly do we, as observers, determine and measure motion and its effects on the objects around us? Consider the case of two trains moving in the same direction at, say, 50 kilometers an hour. For the passengers in each train, the other train appears to be standing still. For people on the platform, however, both are moving at 50 kmph. So the question is, how should we measure the motion? On the basis of the passengers' observations or those of the people on the platform? The answer was that each is right in his own way. The measurement of an object's motion depends on the observer's state, that is, whether he or she is standing still or moving while taking the measurements. In a nutshell, the answer was that motion is not absolute but relative. But if one accepted motion as relative, another question arose. Were all the other laws of physics relative in the way that motion was? For example, if a person traveling at 40 kilometers per hour were to conduct some experiment based on the laws of physics, while another person who was stationary did likewise, would the results be different? The answer was no. As it took shape in the 17th century, the science of physics laid down the first principle of relativity, that whether observed in a stationary situation or while in uniform motion, the laws of physics remain the same. Born in the age of Galileo and Newton, the classical theory of relativity, as this concept came to be known, remained unchallenged until the end of the 19th century, until experiments based on the work of James Maxwell revealed that in a world of relatives there is one constant, the speed of light, which is identical for all observers, whether standing still or moving at any speed whatsoever. While studying the motion of charged particles, he found that the electromagnetic field created by the movement emerged from the particle in the form of waves. Maxwell called them electromagnetic waves, and when their speed was measured, it was found to be precisely the speed of light. One problem that arose immediately was that of the medium. At the time, it was believed that like sound and other waves, light too traveled in a medium. This hypothetical medium was referred to as the ether. But believing in the idea of an ether meant that the speed of light traveling in the same direction as the ether, which was itself revolving with the Earth's speed, would be different from that of light traveling in the opposite direction. But this wasn't true. Michelson and Morley had proved by their experiments that the speed of light traveling in opposite directions was identical. This meant that there was no such thing as the ether, that the speed of light was not relative to any medium but absolute, and was the same in all directions. The turn of the 20th century was a time of great scientific excitement and tumult. The observation that the speed of light was constant created ripples in the mind of one scientist in particular, and the ideas that emerged shook the majestic edifice of Newton's laws of motion by its very foundations. His name, Albert Einstein. Einstein believed that if the speed of light was constant, it had to be so for stationary frames of reference as well as ones in motion, and he proved this mathematically. He said that since speed was the ratio of distance to time, if the speed of light were constant, then to keep it so, distance and time had to change according to the frame of reference.
आइंस्टाइन की रिलेटिविटी में दो कल्पनाएं थी, रिलेटिविटी ऑफ स्पेस और रिलेटिविटी ऑफ टाइम। इनमें रिलेटिविटी ऑफ स्पेस की कल्पना वैज्ञानिकों को पहले से भी कुछ परिचित थी, लेकिन रिलेटिविटी ऑफ टाइम बिल्कुल ही नई थी। तो आप रिलेटिविटी ऑफ स्पेस की कल्पना इस तरह से कर सकते हैं। कल्पना कीजिए कि दो निरीक्षक हैं, एक रेलवे स्टेशन पर प्लेटफॉर्म पर खड़ा है और दूसरा एक ट्रेन में से उसके सामने से गुजर रहा है, जो कि ट्रेन काफ़ी रफ्तार से जा रही है। ट्रेन पर का जो निरीक्षक है वो अपनी एक गेंद ऊपर उछालता है, जो सीधे ऊपर जाके फिर नीचे उसकी हाथ में आ जाती है। लेकिन जो प्लेटफॉर्म पर का निरीक्षक है उसे क्या दिखाई देता है? उसे ऐसा दिखाई देता है कि ये जो ट्रेन है उसकी रफ्तार के कारण जो गेंद है वो सीधे ऊपर जाके नीचे नहीं आती, बल्कि आगे की ओर घूमती है और एक पैराबोलिक ट्रैजेक्टरी में वो ऊपर जाके नीचे आती है। तो ये जो दो निरीक्षकों की दृष्टि में फ़र्क है, ये रिलेटिविटी ऑफ स्पेस से जुड़ा हुआ है। अब रिलेटिविटी ऑफ टाइम यानी दो निरीक्षकों की घड़ियां एक चाल से नहीं चलती, ये कल्पना तो बिल्कुल ही अजीब-ए-गरीब थी, जिसकी आइंस्टाइन के पहले लोगों ने कल्पना भी नहीं की थी।
Through his calculations, Einstein showed that in a moving frame of reference, space appeared to contract, while time would seem to be moving slower. For example, if a meter rod were placed in the train, then, according to Einstein, it would appear shorter for an observer standing outside. Similarly, a watch placed in the compartment would seem to him to be moving slower than one outside. And yet a passenger in the train would find no change in the rod's length or the clock. Conversely, if the observer were in the moving train and the rod and clock were outside, the same phenomena would be noticed. The calculations, however, also showed that such variations in space and time would only be perceptible for frames of reference moving at close to the speed of light. Since the fastest of trains, or even an aeroplane, wasn't likely to go anywhere near 300,000 kilometers per second, we were not likely to notice these phenomena in the normal course of things. This was the long and short of the Nobel Prize winner's extraordinary calculations, and he called it the special theory of relativity. There was a question, though, as there always is in science. Could the principle, which had been established conclusively by mathematics, be seen through actual evidence?
आइंस्टाइन ने अपना रिलेटिविटी का सिद्धांत गणित के रूप में सिद्ध तो कर दिया, लेकिन भौतिकी में यह अपेक्षा रहती है कि ऐसे कोई भी सिद्धांत प्रत्यक्ष प्रयोगों द्वारा या निरीक्षणों के द्वारा जांचे जाएं। तो आइंस्टाइन की रिलेटिविटी पर भी काफ़ी प्रयोग हुए और उनमें से एक महत्वपूर्ण प्रयोग था जब 1977 में नासा ने सैटेलाइट पर घड़ियां छोड़ी, जो कि पृथ्वी का चक्कर लगा के फिर वापस आई। तो इस चक्कर लगाने में घड़ियां जिस चाल से चल रही थी, वो पृथ्वी पर के निरीक्षक के हिसाब से उनको रिलेटिविटी के सिद्धांत के अनुसार धीमे जाना चाहिए था, और बिल्कुल वैसा ही नज़र आया। ये घड़ी जो ऊपर से सैटेलाइट में से घूम रही थी, उसकी टाइम कीपिंग हमारी पृथ्वी पर की घड़ी के मुकाबले धीमी रही, और ये धीमापन रिलेटिविटी के सिद्धांत के अनुसार ही था।
Einstein was the kind of scientist whose ideas were born in the imagination, converted into mathematical formulations, and subsequently proved right in experiments. This was his greatness as a scientist. In 1905, when he wrote his paper on the special theory of relativity, Einstein was working as a clerk in the Swiss Patent Office in Geneva. Around this time, while developing his theories further, he also put forward another revolutionary principle, a principle forever attached to his name in the public mind, in the form of a tiny but profound formula. E is equal to mc squared. Or in other words, mass could actually be converted into energy, and likewise energy into mass. Einstein also said that mass too was relative, and that if an object's velocity were increased, its mass would increase as well.
रिलेटिविटी ऑफ मास ये भी एक अद्भुत कॉन्सेप्ट है, और इसमें हम देखते हैं कि जैसे जैसे वस्तु अपना वेग बढ़ाती है, हमें ऐसा लगता है कि उस वस्तु का वस्तुमान बढ़ता जा रहा है। इसका मतलब ये नहीं कि उस वस्तु का आकार भी बढ़ता जाए, बल्कि उसका वस्तुमान वही बढ़ता जाता है, और ये जो वृद्धि है ये उस वस्तु की ऊर्जा की वृद्धि से जुड़ी हुई है। और आइंस्टाइन का जो मशहूर समीकरण है E = mc², ये हमें यही बताता है कि ऊर्जा में जो वृद्धि होती है उसका परिणाम हम वस्तुमान में होने वाली वृद्धि में देखते हैं, और इसी E = mc² के आधार पर आगे चलकर वैज्ञानिकों ने एटम बम बनाया।
Merely establishing that space and time were not absolute but relative wasn't enough for a scientific mind like Einstein's. One question kept troubling him. How would space and time behave in an accelerated frame of reference? According to Newton, the gravitational pull between two objects was an instantaneous phenomenon, and this applied in the case of the sun and the earth too. But if we imagine for a moment that the sun is suddenly destroyed, then we would come to know of this only 8 minutes later, because that's how long the light from the sun takes to reach us. If Newton were right, and the gravitational effect would instantly cease, we ought to have come to know immediately, which is to say, before the light reached us. This went against the very basic tenet of the special theory of relativity, which was that no interaction or effect could happen at speeds faster than the speed of light. This conflict made Einstein take a fresh look at Newton's concept of gravitation. To do this, Einstein chose the gravitational field exerted by our own planet, Earth. The calculations began again, and the results, when they came, were almost unbelievable. What Einstein was saying was that gravity affected the very geometry of space-time. Our linear conception of space-time had to change, because under the influence of gravitation, the shortest distance between 2 points could be a curved rather than a straight line.
आइंस्टाइन ने जो कर्व्ड स्पेस टाइम की कल्पना सामने रखी, वो समझने में कुछ कठिन लगती है, क्योंकि हम लोग जिस दुनिया में रहते हैं और जो ज्योमेट्री हम लोग पढ़ते हैं वो यूक्लिड की ज्योमेट्री है, जो फ्लैट स्पेस टाइम के बारे में बताती है। अब फ्लैट स्पेस टाइम और कर्व्ड स्पेस टाइम, इनका फ़र्क क्या है, इसे देखने के लिए मैं आपको एक उदाहरण देता हूँ। यहाँ पर आप देखते हैं एक हवाई जहाज का रास्ता है जो लंदन से शिकागो जाना चाहता है। तो इस उड़ान भरने के लिए हवाई जहाज ऐसा रास्ता चुनता है जो सबसे कम लंबाई का हो, क्योंकि इससे पेट्रोल की बचत होती है। तो आप कहेंगे कि यहाँ लंदन है, यहाँ शिकागो है, तो इस सरल मार्ग से, जो कि सरल रेखा को बताता है, सीधी रेखा को बताता है, इसको क्यों नहीं लेता? तो इसका जवाब ये है कि पृथ्वी गोल है, इस पर जो ज्योमेट्री चलती है वो कर्व्ड है, और ये कर्व्ड ज्योमेट्री हमें बताती है कि ये जो रास्ता आपको दिखाई दे रहा है, जो ऊपर जाके फिर नीचे आता है, ये रास्ता सीधे आपको जो सीधा लगता है उससे कहीं कम लंबाई का है। तो कर्व्ड स्पेस टाइम में कुछ ऐसे परिणामों को हम देखते हैं।
What happens is that light does indeed travel in straight lines, but because it travels through space that has been curved by gravitation, it appears to have a curved trajectory. But did this concept, which was applicable to the Earth's gravitational field, apply to all accelerated frames of reference? Einstein's answer was yes. According to him, a person sitting in a room on Earth and one traveling in a rocket through space would experience distance and time in an identical way. He called this the equivalence principle. The concept can also be understood through the thought experiment known as Einstein's elevator. Let's say that for some strange reason, a man decides to travel in an elevator that is hurtling towards the Earth freely, just as if its cable were cut off. The man in the elevator would in no way be aware of the effect of gravity on him or on any of the actions he carries out in the lift. In this free fall situation, he would feel weightless. Inside the elevator, the special theory of relativity would be at work, while outside it, the elevator would be accelerating, and actions and events would therefore appear to be governed by the laws of gravitational acceleration. In this funny elevator, a beam of light decides to emerge from one wall and travel to the opposite one. For the man inside the elevator, the light would appear to be moving along a straight line, but to an observer outside, it would seem to be taking a curved path. The idea of light being bent by gravitation and the associated one of a curvature in space-time was Einstein's second revolutionary contribution to science, and it changed the way gravity was understood. It was a serious challenge to Newton's laws of gravitation, because what Einstein was saying was that it was not really the sun's gravitational field that caused the Earth and the other planets to revolve around it. They were moving that way because space-time itself was curved. This complex idea can be understood with a simple analogy. If you stretch a rubber sheet with vertical and horizontal lines marked on it, and then place a large ball on the center of it, the weight or mass of the ball will make the sheet slope in the center, and the lines around that central area will appear curved. If you then place another ball anywhere else on the sheet, the slope will make it move towards the center. Amazingly enough, the insights of Einstein's imagination were proved correct once again by actual measurements. He became a celebrity overnight when a group of British astronomers took photographs of the total solar eclipse of 1919. They found that they were able to receive a virtual image of a star whose actual position was hidden by the sun. This was happening because light from the star was being bent by the sun's gravitational field so that its position appeared different from where it actually was. Einstein's new conception of gravitation came to be known as the general theory of relativity. With time, more evidence of space being curved by gravity came in. Investigations revealed that there was a shift in the perihelion of Mercury, that is, its closest position to the Sun. Although it was a shift of only 43 arc seconds per century, it was enough to prove the proposition that gravity caused a curvature in space-time. Einstein's new perspective gave science a powerful weapon in its fight to reveal the mysteries of outer space. Today, it is being used to explain such phenomena as black holes, which are believed to curve space-time so radically that light bends 360 degrees in them and doesn't even emerge, as if it were getting swallowed up by the hole like your monthly paycheck. And yet, despite its amazing revelations, Einstein's general theory of relativity didn't smooth out all the curves in the world of physics. Did his ideas mean that there was so much matter in the universe that it bent the entire universe into a closed sphere? Einstein believed this was the case. He believed that the universe was a closed, finite one. But he turned out to be wrong. Evidence subsequently gathered by the scientific community suggests that far from being a closed and contained entity, the universe is an open and expanding one. But then, that's science for you. A journey that seems to follow a straight path at times, only to take a sudden turn in a totally new direction. A journey that takes its course through theory and experiments, throwing new answers to questions and new questions to answers.